So good morning, everyone. This is Zhao. I'm a proxy presenter for this paper, Guitar Gradient Pruning Toward Fast Neural Ranking. So the neural network-based ranking models takes a query vector and a base vector as input and predicts a ranking score that measures how the query vector matches the base vector. Neural networks are flexible in modeling complex relationships among different kinds of objects, such as queries and documents, users and items, or questions and answers. For example, one neural network can model how likely a user will be interested in an item, or a query vector will be interested in a base vector. Given a user vector, ideally we can enumerate all item vectors and compute their matching score with the neural network to recommend the most relevant items to the user. However, real-world recommendation systems forbid the enumeration, as it's often too time-consuming to deploy for online ranking applications over a large number of items. Therefore, neural network-based ranking models are usually used in offline ranking or re-ranking on pre-produced small subsets. On the other hand, in order to apply neural network matching measures in online applications, machine learning engineers design a bi-level retrieval workflow. They first retrieve a small subset of item candidates through simply similarity measures like cosine similarity, using efficient search indices like approximate nearest neighbor, which is ANN search methods. Then, the neural network matching measures are employed over the small candidate set to generate final ranking and recommendation. Fast neural ranking is to use the neural network as the similarity measures in ANN. It's considered challenging because neural network measures are usually non-convex and asymmetric. Traditional ANN search, which usually focuses on metric ranking measures, is not applicable to these advanced measures. As the problem is formulated, given each query vector Q and the neural network measure F, we want to find the highest ranked xi across all base vectors in S. The previous study, SL2G, extends traditional graph-based fast vector searching algorithms by constructing graph indices, for example, HNSW in L2 distance, but searching according to the neural network measure. Here's an example. Each vertex represents a base vector, for example, an item embedding vector. For a given query vector like a user vector Q, we have a neural network fxq to evaluate the similarity or ranking score of a base vector x and q. The value of fxq is color encoded over the space of x. The darker the color is, the higher the similarity of x and q we have. The searching begins from the start point, computes fxq for each neighbor, and makes the neighbor with the highest similarity be the next frontier of the searching. The searching is performed iteratively until no x with a higher similarity can be found. The hedged vertices represent the vectors that we computed neural network measure fxq with. This searching algorithm works well for common similarity or distance measures. However, the evaluation of a neural network is substantially more complicated and time-consuming than a common measure like L2. As a result, in the retrieval problem under neural network similarity measures, the number of neural network evaluations become a dominant factor in execution. So one question can be straightforwardly raised: can we reduce the number of neural network evaluations to improve the search performance? Recall the example, we mark the vertices that are evaluated with the neural network measures as hatched. The actual searching path, which is the red rows, usually follows the vertex that has the highest matching score. Meanwhile, a large proportion of the evaluated vertices are not used in the later search iteration. We can observe that along the searching path, many FXQ computations are wasted since they are far away from the desired searching direction. So we introduced GITAR, a novel graph searching framework to accelerate to searching in the fast neural ranking problem. The proposed graph searching algorithm is bi-level. We first construct a probable candidate set. Then we only evaluate the neural network measure over the probable candidate set instead of evaluating the neural network over all neighbors. We propose a gradient-based algorithm that approximates the rank of the neural network matching score to construct the probable candidate set and present an angle-based heuristic procedure to adaptively identify the proposites of the probable candidate set. We here present the workflow. The major searching structure follows the conventional graph-based ANN searching algorithm, except two places: rank neighbors in line 9 and prune neighbors in line 10. The rank neighbors procedure targets to rank the neighbor vertices such that the vertices with higher ranks include the neighbor vertices having the highest matching score under the neural network measure. On the other hand, the prune neighbors procedure determines the number of vertices that we will evaluate neural network measure on. By the definition of gradient, given a loss function L and a point P, the gradient represents the direction and the rate of fastest increase at point P. When the gradient is non-zero, the direction of the gradient represents the direction in which L increases most quickly from P. Meanwhile, the magnitude of the gradient represents the rate of increase in that direction. We denote the neural network measure is FXQ, where X is the base vector and Q is a query vector. Given a query vector, the fast neural ranking problem targets to find the best k-base vectors that maximize the matching score FXQ from all base vectors. Without loss of the generality, we assume the value range of FXQ is from 0 to 1. We define the loss function L as 1 minus FXQ. According to the definition of gradient, the reverse direction of the gradient is a direction in which LXQ decreases most quickly from X. In the context of the fast neural ranking, the parameters of the neural network F and the query vector Q are given as input. They are both fixed constants. And thus, the only parameters we can optimize to minimize LXQ is X. The reverse direction of the partial derivative of X represents the best direction to search in next iterations. The gradient method provides us with an opportunity to approximate the ranking of the neighbors. We can use the separation angle between neighbor vertex and the reverse direction of the gradient as the ranking criterion. The closer to the direction of the reverse direction of the gradient, the higher the rank it has. Theoretically, when the distance between X and its neighbors are sufficiently small, the neighbor with a smaller separation angle should have a smaller loss, thus leading to a greater matching score. In the proximity graph scenario, the neighbor vertices of X are nearest neighbor of X. Empirically, we can assume that they are sufficiently close for real-world dataset and applications. This figure depicts a visual illustration of the separation angle. For each neighbor vertex, we rank the vertex via its separation angle to the reverse direction of the gradient. We denote the closest separation angle at theta. Alpha is a tunable tolerance parameter that represents how tolerant we are for the neighbor vertices which are not the closest. We select the neighbor vertices within the searching range as the probable candidate set. We use Twitch and Amazon movies and TV datasets. The neural network measure is a deep FM model trained on the datasets. Here is a comparison with SL2G for high recall levels. For example, 95% guitar consistently show a 2 to 4 times performance improvement over the previous SOTA method, which is the SL2G. The algorithm is not very sensitive to the tuning parameter alpha. More experiment and ablation studies can be found in the paper. And this is the final conclusion part. The ultimate goal of the fast neural ranking is to merge the first stage item retrieval and the following re-ranking stage with a complicated neural network into one step. Using a more complex measure may have better effectiveness and lower QPS. We believe the impact of our work is to bridge the gap of the trade-off. In this paper, we introduce a bi-level novel graph searching framework to accelerate the searching in the fast neural ranking problem. The experiment results on public datasets show that guitar consistently outperform the baseline method. And thanks for your attention. For any question, please drop Weijie an email. Thanks.